integrating the pressure forces on a cylindrical container, derive an expression relating the minimal wall thickness necessary to the pressure, height, radius, and tensile strength of the wall material. So let's start with a figure. So we're going to start with a top-down perspective of this cylinder. And we need to find, oh, that's terrible. We need to find the thickness of the wall. So if I can draw a circle, oh my god. So we're going to take the thickness of the wall, represent that as T. And so for this equation, for this expression, I mean, we're trying to find the total horizontal force. So this would be in the positive x direction. And because of that, we're only focused on half the cylinder. And so with each of these forces, we're going to be finding the x component for each of these many forces involved in this half cylinder. So we also need to find the height. And we're just going to this, because again, it's only half a cylinder. So the height, it's pretty simple. This would be the height. So we need to find a way to express tensile strength, and F over A equal to sigma is a way of doing so. So we're considering, for this problem specifically, we're considering the force in the x direction. And so we need to isolate F. We need to move or multiply the area on both sides. So in doing so, we get F, and we're taking the surface area of this outer wall. So that would be 2ht times sigma. We're going to save that equation for later. And so, since we need to find the total horizontal force for this specific section, we're going to need to use an integral. And we can represent that integral as the integral of d of f of x, which can also be represented as integral of pressure times dA. Obviously, we need bounds for this integral, and because we're going from this point to this point using the unit circle, we can make the bounds negative pi over 2 to pi over 2. And we can move p down, that doesn't change. But we need to find a way of representing dA, or every single small little section of area for this outer wall. So I'm going to draw another figure, this representing PDA. We'll also draw the radius as well. So since we need to find the surface area of each small section of the wall, we need to find the arc length for every small angle we come across. And so we can represent that. Well, first of all, this is d theta. This would be the small angles we're taking at each individual point. And so we find the arc length by using d theta times r. This would be the arc length. And since we're only considering the horizontal force, this direction again, we're going to be using cosine theta in the equation as well. And we're also going to be plugging in h because we're considering it, we need to remember that this is a full cylinder, not just a circle, so we need to plug in h as well. So with the equation in mind, we can create the integral from negative pi over 2 to pi over 2 ph r d theta cosine theta. And so now we can derive this expression. And P, H, R are all constants, so we don't need to worry about those. We don't need to change anything from that, but we do need to modify this part, d theta times cosine theta, and the derivative of cosine theta would be just sine theta. And in this case, the bounds of integration would remain the same. And so plugging those in, again, these three variables stay the same. And so sine of pi over 2 is just 1 minus sine of negative pi over 2, that's negative 1. And you are left with 2phr. Rewrite that h. Alright, so like I said, this represents the total horizontal force. And like we figured out before, this is also a way of representing the total horizontal force. So we can actually set these two equal to each other. So we can do that right here. 2h t sigma equal to 2phr. And so we can cancel out a few variables. Well, we can cancel out these two numbers, cancel out the variable h, and since we need to find the thickness necessary, we're going to isolate t, and by dividing both sides by sigma, our final equation would be p times r over sigma.